Okay. So today we will be looking further at the instructions of ARM. And in the first session, we talked about the basic concepts regarding instructions in ARM. And we'll be moving further on instructions today in the tutorial 2. And in tutorial 2, we will be discussing about these topics mentioned on the slide. First, we will be looking at unsigned binary integers and 2's complement, and then signed negation and signed extension, and then stored program computer concept, and then representing instructions. How do you represent instructions in machine code? And then a little bit about logic operations, and finally conditional operations. There we'll be looking at how you can compile an if statement, or and again how you can compile a loop statement. So some of these content you might have already been covered in the lectures as well, but we'll be going through them again. So if you have any doubts regarding them, you can ask them. Just interrupt me at any time, and if you have any issues, even if it is a small doubt, you can use this session, like use this time to get them clarified. Don't move forward without getting them clarified. You can use the chat, of course, if you get into any doubts, issues. Just let us know. So we will start with unsigned binary integers. So some of them might be like simple, so I'll try to complete them quickly, because we are a bit like limited with time. Sometimes maybe if time is limited, we can maybe go for an extra session as well. Anyway, the first thing is to look at the unsigned binary integers. So this thing maybe is simple. So here you are given a number x, and you need to represent that in binary. So so you need to represent the number x in binary, and you all know, like even in maybe O level, A level times, you have seen how to convert a decimal number to binary. You can maybe divide it by 2 and go on, and then get the binary representation of a decimal number. So this is how it is formally written. So you can represent x as this, like more like formally or mathematically, you can represent the binary representation of the decimal number like this. So xn minus 1 into 2 to the power n minus 1 plus xn minus 2 into 2 to the power n minus 2. So this is just a basic thing. And then with this binary representation of decimal, like you can represent decimal numbers starting from 0 to 2 to the power n minus 1 numbers in binary. If you have n bits, like if you have 4 bits, you can go from 0 to 2 to the power n is 2 to the power 4, that is 8, and 8 minus 1 is 7. So you can go up to 7. So if you have 4 bits, you can go up to 0 to you can go from 0 to 7. Likewise, if you have 16 bits, you can do the math and get the maximum number you can represent. So this is like an example is also given here. This is actually a 32-bit number, and if you use 32 bits, you can go to a very large number. And this example is about representing number 11 in binary. So if you look at the binary representation of 11, it will be something like this or 0 0 0 0. The last 4 bits will be 1 0 1 1, and when you apply the calculation or just conversion, you will get the 11 decimal number. And then using 32 bits, I told you, you can go up to a very large number, that is 2 to the power 32 minus 1, and that number is this one. Okay, so this is 4 billion something, which is a very large number. So you can represent all these numbers, and in computer, when you are going to do anything with numbers, the first thing you need to do is to represent it in binary, because computers can store only ones and zeros. They cannot represent decimal numbers directly. So at the end of the day, you have to convert any number into ones and zeros, and that is how you store numbers in computers. So if you have the capability of storing 32-bit numbers, then you can go up to this number. And then the unsigned one is maybe you already have seen, and then you can look at this concept of 2's complement. With 2's complement, you can represent signed integers. Now this also maybe you have seen in somewhere else. Have you? In courses like 2 to 1 maybe, 2's complement maybe you have seen. Anyway, so with 2's complement, you can represent signed numbers. Signed numbers are negative and positive numbers. So with unsigned numbers, it is just only positive. So that there we saw that you can represent only from 0 to that large number. There were no negative numbers represented with the former representation we looked at. So here you can represent negative numbers as well. So that is the benefit here. And of course, in computers, it's not only positive numbers that you will be representing. You of course get the need of representing negative numbers, and negative numbers maybe not just only as numbers you will be using them, but there are other things like branch offsets and other stuff where you will get the need of representing negative numbers. So you need to know how to represent a negative number because of these reasons. So the formal mathematical representation of number x in binary, if you look at it, it will be something like this. So the first term is minus xn minus 1 2 to the power n minus 1. So this n minus 1, xn minus 1 is the n minus 1 bit of the binary representation of x. So if it is not clear, maybe I can go for an example. If it's clear, then we can go forward. If it is too easy also, if I go ahead and explain, then it will be boring maybe. So this is how you represent it. So these other terms are all positive. So xn minus 2 is the n minus second bit of the binary representation that you will be multiplying with 2 to the power n minus 2. Likewise, you will go like all the other terms are positive. The first term, it is negative. So the number, if it is a negative number, you will get a negative answer. And the range you can achieve with this 2's complement and with n bits is this 2 to the minus 2 to the power n minus 1 to plus 2 to the power n minus 1 minus 1. So here you can see that you can the largest number you can achieve is 2 to the power n minus 1 minus 1. Earlier we could achieve 2 to the power n, and there's a huge difference between 2 to the power n and 2 to the power n minus 1. That is, if you divide that large number we saw earlier by 2, it's going to be a smaller number. It's not like subtracting 2 from that. Dividing by 2, like dividing that by 2 will get you a smaller number. So that is because you have to represent the sign as well here. So you can of course represent 2 to the smallest number you can go is minus 2 to the power n minus 1. And here we have given you an example. So this number actually is a negative number. This 1 1 1 1 1. This binary representation is a binary representation of a negative number. And if you do the calculation given here for this specific example, it's going to be something like negative 1 times 2 to the power 31. That is because the most significant bit is 1, and you have to put negative sign, and then 2 to the power 31. That is because here 2 to the power n minus 1. The next one is plus 1 into 2 to the power 30. That is, this one is 1. So all these bits are, so this is x naught, this is x1, this is x2, this is x3. Likewise, you get the idea, right? This is xn minus 1. So if you do that calculation, you will get this number. So the first term will be evaluated to this minus number, and this, all these other bits will be evaluated to this positive number. And if you solve it further, you will get this minus 4 as the decimal equivalent of this binary number. So you can see now we have represented successfully, we have represented the negative number with this notation. And you will see that if this number, the first bit, if it was 0, now if it was 0, this negative part will be 0, right? This negative part will become 0 if the most significant bit was 0. Then the rest, they are all positive. So all these terms are positive, so the resultant number will be positive. So one idea you can get is only if the first bit is 1, you can represent a negative number. And of course, if the first bit is 1, the resultant number will be negative. So that is assured. So that is because the number you are multiplying here is greater than all these other numbers. So anyway, so if the first, like the most significant bit, if it is 1, then it is a negative number. If the first bit is 0, it's going to be a positive number. So that is how 2's complement works, and we'll, like, in a moment we'll see how 2's complement negative, how you can get the 2's complement number if you know the positive binary representation. That we'll look at later. And I think this is clear. So using 32 bits, you can go from this negative number to this positive number, minus 2 to minus 2 billion 147. So this one, earlier we could go to plus 4 billion, but here we can go only up to plus 2 billion number because of this sign representation thing. So that is it. And this also, this we, like I already have discussed, bit 31, or the most significant bit. We call the first bit of binary representation the most significant bit, and that if the most significant bit, or the bit 31, if it is 1, it's a negative number. If it is 0, it's going to be a non-negative or a positive number. So the bit 31 bit is the most significant bit. So we start naming bits, like we name bits starting from 0. The first bit is 0 bit, like, as you get the idea. And then this number, negative 2 to the power n minus 1, you can't represent it with this notation. This number, like if you solve it, it's going to be 2 to the power n minus 1. So the maximum you can go for is 2 to the power n minus 1 minus 1, not 2 to the power n minus 1. So that number you cannot achieve. So that is one thing. And non-negative numbers have the same unsigned and 2's complement representation. So if you get a positive number, so something like 10, maybe, yeah, 10, 20, anything like that. So if you get a positive number and apply this 2's complement representation, or if you try to represent positive 10 in 2's complement representation, it's going to be similar to the unsigned representation. So there's no difference between 2's complement and unsigned representation if it is a positive number, non-negative number. So if it is a negative number, the representation, of course, in unsigned representation, we didn't have any representation for, like, method to represent a negative number. With 2's complement only, you get the capability of representing negative numbers. The point here is that the unsigned representation of 10 and 2's complement representation of 10 are going to be the same. 10 is an example, of course. So some specific numbers are given here in 2's complement representation. 0 is going to be all zeros. There's no difference there. And -1, if you look at it, the -1 will going to be all ones. So you can apply that like the formula that we gave to you earlier in the slide, and you will get that, like you will see that the decimal equivalent you are getting is going to be -1 if it is all ones in the binary representation. And the most negative number is going to be this one, 1000, and this most negative number corresponds to this number, this -2 to, like if it is 32 bits, of course, it's going to be -2 billion this thing, and that is equivalent to this 10000. And if it is some other bit size also, it's going to be the same. The first one is 1 and the rest is 0. And the most positive number, it's going to be the 0. Like the most positive, of course, you can like think of it like, because the positive numbers, they are going to be as similar as unsigned numbers. The only thing is the first bit you have to allocate for the sign. So that is something like a important point. So you, by looking at the first bit or the MSB, you can determine whether it's a positive number or a negative number if it is represented in 2's complement notation. So if the first bit is 1, then it's a positive number. If the first bit is 0, it's a positive. Sorry, if the first bit is 1 or the most significant bit is 1, it's negative. If the most significant bit is 0, it's positive. And by keeping the first bit 0 and changing other bits, the most positive number you can get is this number. That is, you have to set all the other bits to 1. And I hope you get the idea. So this is the most positive number you can achieve. So that is equivalent to this one if it is 32 bits. And if you have any issues regarding these number representations, just let us know, because if we move forward without getting these things cleared out, then it will be hard. Do you have any issues regarding number representation? Derek,
Yes, I also wanted to say the same thing. So if you have any questions at these initial stages, initial topics, please ask and get them clarified, because when we move forward, we will go into more and more complex things, and like I told you, we will implement all these complex things. So you need to have a very clear understanding about the fundamental stuff. Okay, so ask any question, anything that you have a doubt on, please ask and get it clarified before we move on. Kisaru will of course answer anything that you will have.
Yeah.
Any question you have. So give him a hard time, okay?
Yes. So if you get if you have any doubts, just ask. I'll move forward, assuming that you have no doubts. Interrupt me anytime, like if you get any doubts regarding the content we already have discovered or discussed also, you can type it in the chat and I'll have a look. So, and now we are going to look at sign negation here. We are going forward with the 2's complement idea. So 2's complement we'll be using for sign number representation. So that's like a standard. So that the 2's complement is a like a way of representing two negative numbers, and the common standard, or that is like the established standard for representing negative numbers in computers is by using the 2's complement method. So 2's complement, we'll be using it everywhere. So there are other, like, just a side note, there are other ways of representing side numbers as well, but in computer world, in digital electronics world, the common way to represent sign numbers is by using 2's complement notation. So all these sign negation and all that are related to 2's complement notation. And the sign negation is about taking a negative number of a positive number. So you have something like positive 10 maybe, and you need to get the binary representation of negative 10. So if you have the binary number, then you can like calculate the decimal equivalent by using the formula we gave to you earlier. But maybe you don't still know how to get the binary representation of a negative number, positive number. Binary representation of a positive number you already know, like even in A levels or O levels you have seen how to get the binary representation of a positive number. 10, for example, if it is 10, you can start dividing by 2 and then you get the remainder, and you know the idea, right? You get the idea. So that like by hand also you know how to do that, and you might not know how to get the negative tens representation in binary. So that you can easily do with this method we are going to discuss. So here the main idea is about like this the method we are going to use to get the negative number corresponding to a positive number is we first complement the number. Like we first complement the binary representation of the positive number and then add 1 to that. So complement meaning you make ones 0 and zeros 1. That is like not binary not operation. You know what not operation is. So it's like, yeah. So all the ones in the binary representation, you make them equal to 0, and all the zeros in the binary representation, you make them equal to 1. And then finally you have to add 1 to that complemented number. And this the content in this yellow box, it shows like it's like a proof of that we can get the negative number by doing this these two operations. So by complementing the number and adding 1, you can get the negative number. So that is a proof of that. So it's like it's a basic proof anyway. So x plus x bar is the complement. So if you add the complement, can you all hear me? So I got a message saying that my connection is unstable. I hope there's no issue in hearing me clearly. If there's any issue in that also, let me know. So this proof is about that. So x plus x bar, that is complement. You add the complement to the original number x, then you will see. So like you will see that all the like the number you are going to get is all ones. So because if you consider something like 101, then the complement of that will be 010. When you add those two numbers, the number you are getting is all ones. And from the knowledge we gained earlier, we saw that if all the numbers, all the bits in a particular binary number is ones, binary number represented in 2's complement, of course. If it is all ones, then the decimal equivalent of that is -1. And so with this, what you get is x plus x bar is equal to -1. And so if you get minus x to one side, then you will see that x bar plus 1 is equal to minus x. So actually what we need to know is the binary representation of minus x or negative x. So you need to get the binary representation of negative x. You can get that by complementing the binary representation of x and adding 1 to it. So here an example is given to negate plus 2. So plus 2, you all know how to represent plus 2 in binary. So that's very simple. So you can see this is 0, 0, 0. At the end you get 1, 0. And the negative 2 you can get by applying this method we discussed earlier. So you first need to complement it. If you complement this bit representation, what you will be getting is 1, 1, 1, 1 and 1, 0, 1. And when you add 1 to that, the number you are getting is this one, which is going to be the 2's complement representation of -2. Hope it's very clear. If it is like, if there's any doubt, just let me know. So this number you can verify by applying the calculation we talked about earlier, that it is -2. Is it clear to you all? Okay, great. So binary 2's complement representation is all clear, I hope. And if there's any doubt, just ask. And now we'll be looking at something called sign extension. So this also will be helpful in when you are going into lower level stuff, assembly, and then computer, like the compute hardware. So all these things, when you go into these things, you need to know this concept as well. Here it is about representing a number using more bits, preserving the numeric value. So for like, this is like you have something like -4 or +4. It could be minus or plus, and you have represented it using fewer bits, something like 10 bits. Like you might already know, like you can represent a number like 4 with 2 bits. Number like 4, maybe you cannot represent it with 2 bits, let's say 4 bits. You can represent the number with 4 bits. You can represent the same number with 8 bits. You can represent the same number with 16 bits, 32 bits. You know that. So now you have a number represented in 16 bits. Say, for example, you have a number represented in 16 bits. Now you need to represent the same number using 32 bits. So preserving the sign as well. So if like, this could be a positive number or a negative number. So this is not only a positive number we are talking about. If it is just for positive number, you can append zeros to the left. So if you do that, then you can extend it. But here we are talking about both positive and negative numbers. So to do that, all you need to do is to replicate the sign bit to the left. So you need to get the sign bit of the binary representation, and you need to replicate that. If it is unsigned value, what will be replicating is just 0, because the sign bit of a positive number, it's going to be 0, and you can extend the number by just replicating that 0. So that 0 is the sign bit, and if it is 1, that means if the most significant bit is 1, then it means that it's a negative number. And if you replicate that 1 by if you replicate that 1 to the left, you will get the same negative number represented in a higher number of bits. So here it's like a example is given to show how an 8-bit number can be converted into 16-bit number. So you have you have +2 represented in 8 bits. So the binary representation of +2 is going to be something like this: 0000010. If you use 8 bits, now you need to represent the same number with 16 bits. Now all you need to do is to get the sign bit. The sign bit of this number is this first bit. We already talked about that. So this is 0. Now you need to replicate that number to the left so that you complete 16 bits. So that is how you do that. And if you want to extend the -2 represented with 8 bits to a number that is represented with 16 bits, then you need to get still like the same thing you need to do. You need to get the sign bit, which is 1, and you need to replicate it so that it forms a 16-bit number like this. So that is all. So this is all about representing a number with higher number of bits, preserving the sign and the numeric value, of course. So sign extension is about this. Hope it's also clear. If there's any issue regarding that, just let me know. And here, this is like a practical thing you can do with ARM. You can do sign extension in ARM as well. In ARM instruction set, you have these two instructions to support sign extension. Now, the first instruction, the first instruction type is load register half word sign. The instruction name will that is given for that or the short instruction code is LDRHS. LDRHS, that is load register half word sign. And we already have looked at LDR. LDR, there when you are loading like LDR, you used it to load a particular value from memory into a register. So the same thing we will be doing here as well. The only difference is that with LDR, you loaded a full word. When you used LDR, if it was LDR R1, R2 hash 2, so there what you did was you took a full word in memory and placed it in the in one of the registers in the register file. But here we are taking only a half word. A half word, of course, is going to be half of 32 bits, that is 16 bits. So 16-bit half word you are going to get from the memory, and now when you are getting that from memory and placing it in a register, you need to do this sign extension because a register is 32 bits, like that's fixed. So in memory, like when you're loading something from memory, you can decide whether to take the full word or half of that or 1/4 of that. So that you can do, but when you're placing it in one of the registers, it has to be represented as a 32-bit number. Now, when you are placing it in one of the registers, you get the need of extending the sign because you are going to represent a smaller number, like a number represented in smaller number of bits. Small number of bits, you need to represent that same number with higher number of bits. For that, you can use this LDRHS. And the meaning of this one is R1 is equal to memory R2 plus 20. Now that you already know, the main idea here is that you will be extending the sign. So this part actually you know, memory R2 plus 20, that is the offset, 20 is the offset. And similarly, you can load a single byte from memory and extend the sign there as well. So for that, you need to use this LDRBS, load register byte sign. And for that also, you will be using a similar syntax, but the main idea here is that you will be extending the sign when you are performing this instruction. So 8-bit number, you will be representing it in 32 bits because registers are all 32 bits. Hope that's clear. Clear? If there's any issue, just let me know. Okay, so now here we are going to look at a new concept. Now all this number stuff we are done with them. Sign numbers, unsign, and then sign extension, all that we already do at, and then stored program computers. This is a new concept. So this concept is about a small, like the concept might look small but simple, but it's very common in computers and all the devices, computational devices. So the idea here is that instructions represented in binary, just like data. So data, all these examples we looked at were regarding numbers. So numbers, we consider them as data, basically. But instructions are it is going to be the code of your program. So it is not the data, but the instructions. So instructions, we already have looked at them now, add, sub. So those instructions, we already have looked at them. So these instructions are also going to be represented in binary. When you are going to execute a program using a computer, the first thing you need to do is you need to encode instructions in binary, and they are going to be stored in memory just as binary numbers. So when you just look at the memory, you will like not see a difference between an instruction and a data, because they are all going to be ones and zeros. They are all represented in binary. And okay, we have a question. Maybe I'll complete this slide and go back to that. Good that there was a question. There's a question. So here the idea is instructions are going instructions are also going to be represented in binary, just like data. And instructions and data, both of them are going to be stored in memory. And then the next idea is programs can operate on programs. So programs are like, there are programs, things like compilers, linkers. So they are programs, and they are also written using instructions. And those programs can so there are like, these are specific programs, compilers and linkers. They are specific programs. They can operate on other programs. So if you take compiler, for example, it's going to take your C code, so that, which is also a program. So if you if you look at C compiler, GCC compiler, that's a program actually which operates on another program written by somebody else. So that also can be done in this stored program computer concept. That also happens actually, and at the end of the day, that the second program also will be converted into binary, and they are all going to be stored in memory just as ones and zeros. Binary compatibility allows compiled programs to work on different computers. So this is about the ISA, which is standardized. ISA is instruction set architecture. That also, this idea also you already know. Instruction set architecture idea you already know. And then if you have a standardized ISA, and if you like, when you are doing this compiling process, you are going to get a program that can directly be executed on the computer, which is a program in terms of ones and zeros. So they like a program in machine code. So machine code basically means ones and zeros. So the program at the end of the day is going to be converted into ones and zeros. The instructions are going to be converted into ones and zeros. And if you have a standardized ISA, you can get a compile code in, like a compile code compiled into an Intel processor. You can get it from one place, and you can put it on another computer that has the same processor, Intel processor, for example, and you can run that compiled code, compiled binary on that second computer without any issue if you have a standardized ISA. So if the ISA is standardized, you can do this. And this is the big picture is given here in a diagram as well. So processor, you have it, and in the memory you will be having the binary representation of the instructions of a program called accounting program, and there could be an editor program which also resides in the same memory, and C compiler, which is also a program. So that compiler, that program is a specific program which operates on another program. So it's anyway going to be represented in machine code when you put it in the memory. And payroll data. So this is going to be data, payroll data. So the salaries and all that, you will be putting them all in memory. So this is not a program data, but it's also going to be represented in ones and zeros in memory. Book text, source code in C4, editor program, all that are going to be stored in memory. And it is the operating system and the software that treats them as either as a program or data. So that is the main idea here. Everything you store in a computer has to be stored in binary. It could be a program or data. And we'll go to this question now. Really R2 hash 20 means what? We use the same in both. What is the difference between them? Yeah. So like in both these instructions, we are using the same what do you call this memory operand part. This R2 hash 20 part, it is the same here as well in all the cases. Even in LDR, we use the same thing. So I'm answering this like Dushinta's question. so R2 hash 20, this thing is same because we are going to get data from memory, which is at this specific location. So R2 contains the base address, as we discussed in the previous session or the previous tutorial. R2 contains the base address, and we are going to get data which is 20 bytes away from this base address in R2. So yeah, that is what you mean by this R2 hash 20. That is R2 plus 20. But when you are getting data from memory, you can, like, you have the option to get a full word from memory, or to get a half of that, or to get 1/4 of that. So that option you have. The location you are looking at is the same, but the amount of data you are getting from that location, it depends on the instruction type, the specific instruction type you are using. Now, for example, can I draw things here? So say you have something like this stored in memory. Okay, so this could be a memory location. Memory could be something like this, and this in the at this specific memory location. R2 plus 20 location is here. Okay, R2 plus 20 location is here, and now you need to get the data stored in at this particular location and load it into a register. Here in this example, you had to load it into R1 register, and when you just execute a normal LDR instruction, what it will be doing is it will take the full ABCD number and place it in R1 register. Okay, R1 register is there on the in the processor. So we have R1 here in the processor, and if you have if you execute this LDRHS instruction, it will be still looking at the same memory location, but it will be taking only a half word from this word. Okay, so in memory, actually, if you look at the memory, it's going to be something like this. More precisely, it will be something like this. This D is this little endian and big endian notation, all that we discussed, I hope. So in ARM, you use little endian notation where you store the least significant byte in the lower address. So R2 plus 10 is going. So this is the R2 plus 10 address. This is like the R2 plus maybe I'll use here. R2 plus 20 address is here. This one is R2 plus 20, and this one is R2 plus 21. This is R2 plus 22, 23. So we discussed that when you are taking a value from memory and load it in one of the registers in the register file, instead of just 1 byte, what it will be doing is it will take a full word and place it in R1 register. That is why we had to, when like in memory offsets, if you want to get the third element, you had to multiply 3 by 4 to know the memory location of the next element, third element. So likewise, we already looked at that idea. So maybe this one will delete it. How can I clear it? So this is like a more more precise representation of memory. So when you say R2 plus 20, LDR R2 plus 20, then it will be taking the full word in the memory and place it here. And if it is LDRHS, it will be taking only one like half word. Half word is, this is the full word, and half word is 8. It's 16 bits, and it is 2 bytes, of course. So these two bytes, it will be taking these 2 bytes and place it in the R2 R1 register. So it's going to be CD, and the like the important part here is when you are placing this using this instruction, it's going to extend the sign as well. So for that you need to is there any question? Anybody trying to ask me? So this CD, you are going to place them in the R1 if you execute this LDRHS instruction, and this C. So the sign extension thing. Now all these numbers, I'm representing them in hexadecimal to make the life easy. Otherwise, you have to write all the ones and zeros. So if the C, if you take C and try to write the binary representation, what is it? Can somebody help me? What is the binary representation of hexadecimal digit C? Any idea? Okay, 12 and yeah, 1100. Yes. So C, like number C, you can represent it using 1100, and D, of course, is going to be something like 1101. So these are the things that are going to actually be stored in the registers, memory, and all those places. So this hexadecimal representation. So in hexadecimal representation, we are using this is like a compact way of writing binary numbers that already we have discussed. So C and D are going to be represented in all these places like this. And if you consider this C, now C and D, like this half word we loaded from memory, it's 8 bits. Now you need to extend it to 32 bits because the register is 32 bits, and you have to represent it, like you have to put it in R1 register as a 32-bit number. Now, when you execute this instruction, what it does is it extends the sign of this 16-bit half word. So when it is doing that, what it does is it does the same operation we've been talking about earlier in the sign extension theory part. So this one, it will take this one and it will replicate this bit into other 16-bit locations. So the rest of the R1 will be filled with this most significant bit. That is, this sign bit will be replicated 16 times. Do you get the idea? When you replicate it, it's going to be 1 1 1 1 1 1 1 1. So if you look at the R1 register after you are done with this particular instruction, it's going to look like something like this. It's going to look something like this. So,
excuse me, sir.
Yeah.
The C and D together will be having 16 bits, no, sir? Yes.
Yes, right.
So why did you put it as 4 bits for each one?
I'm sorry. Yeah, I did a mistake, kind of like a mistake, because one byte is going to store 2 hexadecimal digits, right?
Yes.
Am I right?
Yeah.
Yes. So the instead of these A, B, C, D, just like hexadecimal numbers. So if you are going to represent it with hexadecimal, then you have to put some other letter as well here. Good
Make it
that you
A,
noticed.
B, B, C, C,
Yeah,
and D,
yeah,
D.
yeah, yeah. We'll consider them as
Yeah.
D, D, C, C, B, B. I'm sorry, I missed that point. Thank you. So I missed that this is 8 bits and not 16 bits. That also I missed. So this is 6. This is 8 bits. So what you need to do is, how can I erase it? Yeah. Okay, we'll get this one. Now for DD, it's going to be like 1 1 0 1 1 1 0 1, and here it will be this is for DD, this R2 plus 20 thing, and here also you have to make the correction. CCDD, and the rest is, so you have to like, this is like the double size of this part. So this is it, and 0 0 1 1 0 0 1 1. Okay, this is CCDD. Now you have to extend the sign when you are loading it to the register using this instruction, this particular instruction. So you get the most significant bit of this CCDD number and you replicate it how many times? 16 times. Now it's going to be 1 1 1 1, all ones, 16 bits. And if you represent it using hexadecimal, it's going to look like something like this: D D C C, and here you will have F F F F. So this is exactly the, this is essentially the content in R1 now. This is R1. Okay. Since we don't have space, enough space here, I'll remove it here. And so this is how you load by half word from memory and extend the sign. So is it clear now? And if it is just about LDRBS, which is about load register byte sign, you will be loading only 1 byte and extending the sign. So you will take the byte stored at R2 plus 20 location, which is in this example DD, and extend the sign there. So in DD also the sign bit is going to be 0. So sorry, 1. So you have to replicate the 1 how many times? If it is load register byte signed instruction, how many times do you need to replicate the sign bit? "24 times, right? Are you following? Are you all following?
Yes, sir.
You are following, right? The one who asked the question, is it clear
Yes,
now?
sir.
Okay. Now I have got a private question as well. R2 plus 20 means 5 blocks, 4 into 5. R2 plus 20 does not mean 4 into 4. Answer? Maybe I'm not clear about the question. So R2 plus 20 means just the starting address of the memory location we are going to access. So memory is addressed from 0 to the highest number you can go for with that specific size of memory. So it starts from 0, 0, 1, 2, 3, 4, likewise, and each byte in memory is given a unique address, that is 0. The memory location 0 is going to store a byte, and memory location 1 is also going to store a byte. So here in this example, R2 plus 20, so it's going to store a byte. And when we are specifying these things in LDR and str instructions, what we are telling is the memory location we need to access. That is like the actually starting the starting memory location of the memory we are accessing. So if it is just LDR, you will start with R2 plus 20, but you will be loading a full byte, full word from memory instead of just the byte located at R2 plus 20. So this of course is going to be R2 plus 21, and this location is R2 plus 22, R2 plus 23. So these are going to be like that. So if you like in the like the array examples we saw earlier in the previous tutorial, we used the like we were going like jumping 4 likewise. So if you want, when we wanted to access the next element, we used 24 as the offset. That is because the next element is going to be starting from R2 plus 24. Maybe some doubts you had in the previous tutorial also are cleared, I hope, with this explanation. If not, just let me know. So this is how memory is going to be addressed, and this is what happens when you load something from memory located at a specific location specified by this memory operand. And if it is just LDR, it
And
will
guys,
be
sorry, Kisaru. So
yeah, sure.
It's good that you're asking questions and getting your doubts clear. That's what we want you to do actually.
Yeah.
And I just wanted to say that you're in the coming labs, lab 4, I think you will be dealing with the instructions which are used to access data in memory, reading and writing to memory. So instructions like LDR, storing, loading, storing, half words, bytes, all those things you will be spending a lot more time on it. So yeah. So
Yeah.
the specific
So if
mechanics of loading half words bytes you can worry about there, but you need to have an understanding how the memory is laid out at this stage. Sorry about bumping it.
yeah, that's all fine. So hope the memory layout and how it is addressed and all that are clear now. So this is how it is done. So when you are accessing R2 plus 20, it is a memory location that you are going to access. And if it is the specific instruction you are using, if it is LDRHS, then you are going to take only one, then you are going to take only half word, not the full word you are going to load from memory. And if it is LDRBS, then you are going to take only 1 byte. So in like when you are using these things, you will actually maybe when you are using them, you might not see what's happening inside, but the idea or the thing that is happening on the with memory and processor is this. Hope it's clear. If we need to get BBAA, BBAA R2 hash 22. Yeah, it's correct. But now there's something called memory alignment in ARM. So you can execute this instruction and see whether the assembler also does some stuff, and it tries to achieve the thing that you're asking the processor to do. So it will perform this instruction, but if it considers memory alignment thing, then all your offsets have to be multiples of 4. So if they are aligned to 4 bytes, then they are going to be they all have to be multiples of 4. So maybe if you need to get the most significant part of this one, you can perform other operations as well to get that. Maybe not with one instruction. You first need to load it and then you can shift it. So bit shifting also we'll discuss later. Dushin asked it, right? Dushar. So you can try executing this instruction on your computer and see, Dushin, whether it works. So if memory alignment is not handled, like if it is handled in another way, then it is going to be okay. And we are getting private questions as well. If like when you're asking questions, it's better if you put it in a way that everybody can see. So that is in this two field you put everyone. In LDRBS instruction, what byte it will get. When you execute that, when you execute LDRBS, it will be getting the least significant byte, not the other ones. Just like it was in the half byte example, it is getting the lowest byte because the lowest byte is stored in this R2 plus 20 location. So if you say R2 plus 20, it will start getting stuff starting from that address. And if it is just 1 byte, it will get that byte which is located at that specific location. 21. Yeah, Shamal also has asked the same question. So if the memory alignment is checked by the assembler, you are only able to give multiples of 4 as offsets. So in that case, you need to first load the full byte or the full word into the memory and do shift operations, and bit masking and things like that are coming. So those operations you can do to get the other bytes. So yes, correct, exactly. Manohara, I think. Yeah, your question, the answer to that question is yes. If you, when you use it, when you use LDR, what happens is you get the full word from the memory. A, A, B, B, C, C, D, D. Hope that's all clear. Okay. Now it's good that I asked that question. So hope there were the doubts as well regarding to that. We'll quickly go through this. So if we need for extra time, we'll look for an extra session. Representing instructions. Now comes to the point where we are trying to represent instructions in a binary. Now all the stuff we discussed so far were mostly about data. That is the numbers. Numbers are the data. Now we are looking at how you can represent instructions in binary, because in stored program concept we talked that you have to represent instructions, data, all that in binary. That is the only way you can represent stuff in low level hardware. So these instructions encoded in binary, we call them machine code. So machine code is the code that is going to be executed by a processor. Processor cannot understand anything other than ones and zeros, electrical signals. So if you look at ARM instructions, they are all encoded as 32-bit instruction words. So every instruction, it's going to represent it in 32 bits. So variable, it is not variable length. That is a property of RISC processors as well. You all know ARM is a RISC processor. Small number of formats, encoding operation code, register numbers. So there are small number of formats, instruction formats, encoding formats, which encode the operation code, register numbers, and all that. So you will actually see how an instruction is encoded in binary. Soon you will see all that, how a memory operation instruction is encoded in binary. And regularity. So they are all, you can see all these instructions are 32 bits in size, and the way the formats are, like the way the formats are organized, all that are regular. So regularity is there. And register numbers, we all know the register numbers we have in ARM are from R0 to R15 because we have only 16 registers. And this is the first instruction encoding format you are going to see. This is ARM data processing instructions, how a data processing instruction is encoded in binary in ARM. Now, when you are going to represent that instruction in binary, the instruction is going to be split into 1, 2, 3, 4, 5, 6, 7, 8 fields. So it has been like when you look at the 1 and 0 instruction machine code, you won't see anything that separates all this. But for clarification, and anyway, the organization is going to be something like this. And when you are going to build a hardware that can execute these instructions, you need to first decide on the instruction format. And so based on that format, you will be extracting particular bits, and you will design hardware so that a particular instruction is executed properly. So anyway, the instruction encoding is going to look like this for a data processing instruction. Now, data processing instruction is an instruction. So the data processing instructions are usual arithmetic instructions that you have seen. Things like add instruction, sub instruction, so those things. And data then if you look at the different fields of this instruction, the first one is condition if I opcode is rn rd operand 2. So this opcode means the basic operation of the instruction, and rd field, it encodes the destination register operand number, so the register number. So we all have seen this add r1 r2 r3, so they are the destination register was r1, the first argument to that register, to that instruction was the destination register. Now that destination register number is going to be encoded in binary, and it's going to be stored in this particular location in the encoded instruction rd. Now here you can see for rd and rn, you have only 4 bits. So we have allocated 4 bits for these two sections in the instruction. That is because why? What? So we only have 16 registers. So to encode the number 15, so the numbers that are going to be put here are going to be from 0 to 15 because the register numbers we are putting here, and 0 to 15 can be encoded in 4 bits. If you take 4 bits, the maximum number you can represent with 4 bits is 15, and the lowest is 0. So you can successfully encode the register numbers. And operand 2, if you look at the operand 2, the second source operand, now this second source operand, it could be a register number or a immediate value as well. Now we have looked at immediate operands as well. So those immediate operands are immediate operands or the second source register number. They both are going to be stored in this operand 2 section. So depending on the instruction you are using, it could be a register number or a immediate value. Now, to differentiate between if it is a immediate value or a register number, you use this field, this I field. If that 0, like if I field, if it is 0, now it's a 1 bit, of course, you can see that. If this bit is 0, this operand 2 is taken as a register. And if I is 1, that is to say that we are going to use an immediate operand with this instruction. So if it is 1, then this operand 2 field is going to be treated as an immediate operand. Now you can calculate the number, the maximum number which can be stored here to get an idea about the maximum immediate operand you can use in an instruction. So 2 to the power 12, of course, 2 to the power 12 minus 1. And set condition code. So these other fields are there. So these things maybe we'll discuss later as well. Condition code also we'll discuss later. And instruction format, this this part we use it to differentiate between different formats. So we have different formats. Now data processing format is one format, one such format. So there are other formats as well. As we go on, you will see other formats to access memory and all that. We need different formats. So those are encoded in this F field. And here is an example for data processing instruction encoding format. Here it's an add instruction. You can see we are trying to encode an add instruction. This specific instruction, what it does is R5 equals to R1 plus R2. The instruction we are using is add R5, R1, R2. Now here in this instruction, R5 is the destination register and R1, R2 are the source registers. So those numbers, this 5, 1, 2, those things are going to be encoded in binary, and that is what at the end of the day is going to be executed on the processor. So now condition code, it's going to be a constant value for all the data processing instructions. Add, sub, for all that we'll be using 14 as the condition code, because there's no any meaning like to have a condition in data processing instructions. You will see how condition is used in so there are other instruction formats that make use of this condition field, but data processing does not make any useful use out of it. So, and F field, because this is the first format, we are using 0 here, and immediate is 0 because we are not using any immediate value in this instruction. And for here, you can see it's therefore the opcode. So opcode also is defined as 4 for this add instruction. So you will see when we come to the implementation of a processor, small processor, you will see that this opcode is very crucial in determining the type of instruction and all those things. So you need to pay a lot of attention in these 1, 4, 2 fields. So here you can see the destination register is 1. Sorry, Rn. Rn was the first source operand. Rn is the first source operand, so that is R1. So we are putting 1 here, and RD is the destination register, that is 5 here. The destination register is 5 here, so we are putting 5 here in this RD field, and 2 we have put it in the second, the last part of the instruction, because the operand 2 is going to act as a register number, not as an immediate value. So the register number we need to encode is 2, so that is put here. Hope it's clear. And if you get the full binary representation of this instruction, it's going to look like something like this. And so this is exactly what is going to be executed in the processor at the end of the day. Real hardware, like it can understand only ones and zeros, so we have to encode instructions as well as ones and zeros. So it's clear, I hope. And now this hexadecimal notation, now only we like officially discuss about hexadecimal notation, but I hope you already have an idea, because that I think you have used in C course as well. So hexadecimal notation, we use it to use it as a way of representing large binary numbers in a compact way. So base 16 hexadecimal compact representation of bit strings, 4 bits per hex digit. So a single hex digit is represented in 4 bits in binary, and you have this table to know the mapping between hexadecimal digits and binary. Earlier we used things like A, B, B, C, C. Now you can see here. A is 1010, B is 1011, C is 1100, D is 1101. So all these mappings we used in the previous example as well. So now this an instruction like this is a 32-bit number, and it's a lengthy binary string, so that you can represent in a compact way by using hexadecimal notation. So yeah, 32-bit binary string you can represent using hexadecimal like this, EC8. Hope you get the idea. And if you have any questions related to these things, also just ask, just like you asked about ask questions about the previous part. If they are too simple, also if I go on explaining a simple thing again and again, then it's going to be boring and also time consuming. And So data transfer instructions. So this is now data processing instructions. We looked at that format, and now this is data transfer instructions. This is the type of instruction that deals with memory load, store, and things like that. So an LDR instruction, for example, is going to be encoded in this format. So here you can see the condition code is similar to the condition code we saw in data processing instruction, and there's this format field to represent the instruction format, and then opcode and RN, RD. So those things are there, and you know, there's no need of having a second operand for a data transfer instruction. So that part we are using it as it to encode the offset. Now we have seen these offsets, so we looked at them just a little while ago as well. Now, if you take this LDR R5 R3 hash 32 as an example, what you are trying to do is you take the value stored in R3 plus 32 location in memory and load it to R5 register, and those things you can encode in the instruction according to this format. R5 is the destination register, so you are putting 5 as the number 5, you are putting in the RD field, and of course this 5 has to be represented in binary. And then offset is 32, so 32 you are going to put it here, and RN is the first source, so that source we are using is R3, so 3 is put here, and format is this is a different format. So earlier we used 0 for data processing instructions. For data transfer we are using 1, and the rest, like the opcode, the full opcode here what we are using is 24, and immediate value is being used. Now it's also included in this opcode. So now hope you are clear about how you can encode a data transfer instruction, which is basically a memory load or store instruction. Now I have a question sent privately to me. Is I can't use an offset more than 12 bits. No, yeah, that is also a good observation. So the maximum offset you can have is 2 to the power 12 minus 2 minus 1. Sorry. So the maximum you can use a offset made up of 12 bits only. If you want to go for a larger one, then you can think of maybe changing the base address. You can change now. Base address you can change, and then go and change the offset accordingly. And now here we come to another design principle. We already have looked at 3 design principles earlier. Design principle 4 is good design demands good compromises. Now if you look at the concepts we have discussed so far, you can see different formats could complicate the decoding process, how a instruction is decoded. So because we already have looked at 2 different formats, so there are other formats as well. So so different formats are there, but it allows 32-bit instructions uniformly. So the benefit here is that you can have 32 bits for all the instructions. So when you that is like a trade-off. So that is like a compromise. But uniformity is more important when you go for designing a real hardware that can execute these instructions. So you can gain speed and all that when you are having a uniform structure for the instruction. So because of that, we have different formats, instruction formats. And when we are doing this, we are going to have different formats, but one thing we need to keep in mind is to keep formats as similar as possible, so that the decoding process becomes easier. So even though it's complicated, it has become complicated, you can make it a bit less complicated by keeping the formats as similar as possible. So this is the design principle 4, and now we come to the logical operations section, where we talk about the instructions that can be used to perform logical operations. So we have already discussed about the arithmetic operations, add, sub, and things like that. So these are not very what do you call, complex stuff. This is just about the instructions that we use to perform operations like bitwise and, bitwise or, bitwise not, shift left, shift right. So all these operations, we call them logical operations. And in C, you use this and sign to perform bitwise and then in for O you use this sign, and for shift you use this sign, and all that. So in Java, it's almost similar. Yeah, in the Java and C, you use the same syntax for all these operations. And in ARM, all what you have is just instructions. You don't have these signs, because you can only instruct the computer or the processor to do this stuff. So to instruct the computer, you will use these instruction codes and code. So add code you have already seen, and you can use for AND, bitwise and for bitwise or you use ORR. For not, you use move not, MBN, and for shifting left you use LSL, and for shift right you use LSR. So these are bit operations. Yeah, I think what shift left means and all that. So you shift the bit string one bit to the left, like shift it to the left one time. Shift left 1 means shifting a bit stream to the left, and shift right means shifting a bit string to the right. Useful for extracting and inserting groups of bits in a word. So some of these instructions are useful for extracting and inserting groups of bits in a word. So that also we'll discuss now. Here you can see how AND operation can be used to mask certain bits stored in a particular register. So for example, now here you have we can maybe go directly for this example so that you understand the idea better. With this, you can select some bits. Select masking meaning select. You can select certain bits in a register and clear other bits to 0. Now this instruction, and for example, and R5, R1, R2. So you need to get the bitwise AND operation between R1 and R2 and store the result in R5. Now what we are trying to look at is the result stored in R5. If you look at this example where R2 stores this particular bit stream and R1 stores this particular bit stream corresponding to a particular value, decimal value. So if you perform the AND operation between these two values, then what you are going to get is these are going to be 0, 0, 0, and is 0, that you all know, and 1 ANDed with 0, it's also going to be 0. So bitwise AND meaning you take each bit pair and perform the AND operation and put that in the result. 0, 0, likewise 1, 0, 0. So when you look at this particular set of bits where R1 stores ones in those bits. So when you perform 1 AND with 1, you get the original bit that you had in the R2 register as the result. So when you AND something with 1, you get that something as the result. So that is the main idea here. When you AND 1 with 1, you get 1, 1 with 1, you get 1, 0 with 1, 0. So what we need to do is take only these 4 bits and put them in the result while clearing other bits to 0. So that thing you can do with this AND operation, bitwise AND operation. This we call bit masking as well, because you are masking a certain set of bits out of a register. So actually we are masking these 4 bits of R2 with the help of this. R1 register. Hope that's also clear. If there's an issue, just ask. So register number is a 32-bit number. All those basic concepts you already know. And operation, you can use it to include certain bits in a word. So that is like setting certain bits to 1 deliberately while keeping others unchanged. The rest of the bits, you don't do anything to them. You have to keep them, leave them unchanged. Yeah, so for that you can use this O operation, bitwise O operation. So that is 0, 0, 0, 0, this string. So this one, you need to make these 4 bits equal to 1. Deliberately, you need to make them equal to 1 while keeping others unchanged. So these bits are unchanged. You can see in the resultant result, you can see they are all the same. They have not been changed. And then these ones, these 4 bits are changed. So R2 is it is the main value of focus. So this value, this bit string, you need to make 4 bits of this particular string equal to 1 and keep the others unchanged. Hope that's also clear. If not, let me know. And not operation, this is like a very simple thing. You can use it to invert bits in a word. Change zeros to 1 and ones to 0. Complementing. ARM has moved not instruction that can be used for performing the not operation, MVN. And for MVN, of course, you know, you only need to have 2 operands because you just take the not of one operand and put it in the destination operand. Here you can see 0, 0, 0, all zeros. Like the R1 register is inverted and it is put to R5 register. And then we come to the shift operation. So logical shift left, you have shift left and shift right, 2 main operations. And with logical shift left, you can shift left a bit string. You can shift. Okay. Can you explain about the mask bits again? Sure. This one, right? Okay. Maybe this is the first, since this is the first time you are learning these things, they could like they could look strange to you. So it's good that you ask questions. So this one we use it to now this R2, like we have a certain bit string, something like 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1. Maybe like I'm taking a small example, 1, 0, 1, 0, 0, 1, 0, 1. This is all zeros and 1. Okay. Now we need to mask these 4 bits for whatever reason, like reason you will understand them maybe later. For a certain application, we need to know the mask out these 4 like specific 4 bits, that is starting from 0, 1, 2, 3, 4, starting from 4th bit to 5, 6, 7 bit, 7 to 4 bit, 7 to 4. You need to mask these 4 bits, that is you need to get the value of these 4 bits. Value of these 4 bits meaning, actually basically what we will be doing is we want to get these 4 bits in the result 0, 1, 0, 1 while clearing other bits to 0. So you have to, like here you can see other values are there, 0. They are all not zeros. So these 4 bits anyway are zeros by default, but these 4 bits, if you look at them, they are something else, 1, 0, 0, 1. So they are not zeros. And here also 0, 0, 1, it is not 0. It is not all zeros. But in bit masking, what we need to do is to get, like extract these 4 bits. Maybe that is the word which is familiar, more familiar to you, extract. So you need to extract these 4 bits and put others to 0, clear other bits to zeros. So you need to make these bits, these 4 bits 0. So 0, 0, 0. Okay. Now here these 4 bits also you need to make them equal to 0, 0, 0, 0. And these 4 bits also you have to put them to 0, but anyway they are originally 0. So these 4 bits are preserved and the rest are cleared to 0. To get this behavior done, what you can use is this AND operation. So so this is our target. Like you need to mask out these 4 bits and put the result into another register. So this is our register R, say R2, and we need to get the value of R2 and mask these, extract these 4 bits and put it in R5 register. Okay. So now for that, what you can do is you use this bit string 0, 0, 0, 0, 0, 0, and at this particular location, you will have 0, all zeros, right? These are all zeros, and here for corresponding like that. For that, you need to, of course, use another register. With only these 2 registers, you cannot perform this bit masking. We need to we get the need of having an extra register which stores this particular bit stream 1 1 1 1 1 1 are going to be at these places, and the rest are going to be all zeros. 0 0 0 0 0 0. And if you like this value, we are going to store it in R1 register. And now with AND operation and the logical AND instruction, you can perform bitwise AND between 2 values. So that is the benefit, like that we have, that opportunity we have. So we can get the bitwise AND between these 2. If you get the bitwise AND between these 2, you will see that you can get this answer in another register. So in this example, R5. So when you get the bitwise AND meaning, you take each bit, like bit pairs actually. Bitwise AND meaning, you get the 0th bit or the least significant bit of R1 and R2 and do the AND operation between those 2 and put the result in the 0th bit in the result or the destination register, and you then go for the first bit and go for the second bit pair and third bit pair. Likewise, bit pairs, you will get those bit pairs and perform AND operation and put the result in the destination register. So when you do that, you will see that when you have something like this setup, like R1, for R1 you have put this particular bit stream, and in the R2 you have the original bit stream of which you need to extract certain bits, and then you perform the bitwise AND. Then you will see that in these places R1 contains 1. So when you AND something with 1, the idea is when you AND something with 1, you get the original value back in as the result. That I think is like a basic idea. So when you AND anything with 1, you get the original value. So that is what is happening here. So when you AND 1 with these 4 bits, you get those 4 bits back in the result. The others are clear to 0 because when you AND something with 0, the result is going to be 0 always, right? So no matter whether there's a 1 here, 0 here, they are going to be forced to 0. That is what is happening here. So this is like a larger version of this same example we discussed. Is it clear now, Shamal? Shamal, is it clear or do you need further clarification? Hope it's clear. If you like think about it again, like look at it again and see how it works. Like it's a nice thing that is happening. So this and operation is a simple operation, but with that you can get this done. You can mask certain bits out of a certain number. So R2 is the number of focus, and with O it is like the other way around maybe. Yeah. Yeah. Is there a specific order or a procedure when masking bits? Mask, no. There's no like this operation does not know whether it is like this AND operation does not know whether it is used to mask bits or actually to perform a bitwise AND. That they don't know, but the bit masking is like an application of this AND operation. So the order actually is the order. I'm not as of what order. So order is, if you think about, like if you mean the order in which the bits are ANDed, then it's going to be the respective bits, that is 0 0, the 0th bit with the 0th bit of R1. There's no procedure as such, like you can just use the AND operation, and you can actually interchange these two source operands, because you will you can see, even if the R2 contain this value and R1 contain this value, then you will get the same result. So it's like what do you call, it's like a like a logical thing that you first need to do, like you get the need of masking bits, and then you put proper. How do we know which bits to mask? That all depends on your need. Actually, you are the one who decides which bits to mask. So now here you have decided that these 4 bits should be masked out. In R2 you have a particular bit string, and you decided that I need to mask out these 4 bits, and while clearing others to 0. So that is the need is coming from you. For a particular application, you get the need of masking out these 4 bits. So now you decide on the string, the bit string that you need to be used to AND this with, and that you have to then put into another register and perform this operation. That's all. So which bits to mask, that depends on your application, and then you need to set the registers up accordingly. Hope it's clear. Maybe with an example you will understand it. Example for an application. Yeah, good that it's clear. Actually, these concepts will be useful in your upcoming courses as well, like embedded systems course, for example. Now these casual instructors, they know well, because they are using these bit masking for some stuff. So these ideas you need to have in your mind, because they are going to be useful in other places as well. So these basic low level concepts. So yeah, so shifting, we were discussing about shifting. Yes, exactly. Now an example has been suggested by Shirley. So in networking, we extract network address from IP. For example, you have done this networking course, right? Hope you have so you have an idea about that. So in networking, you need to get the network address using an IP, and for that you need to perform a masking operation similar to this. So yeah, that's a good example application. So routers and all are also going to be using these processors at low level. So they'll be using these operations for that, for those kind of stuff. And shift operation, we'll look at it now. Shift left, if you consider shift left, it's going to shift a particular bit string to left, and the remainder will be filled with zeros. So, and in logical shift right, you shift a bit stream to right and fill the remaining bits, or the bits that are going to be vacant, in other words. So those bits will be filled with zeros. So that's how shifting works. Do I need to draw that, the how shift operation works? If it was not clear to somebody, let me know. And since these are basic concepts, we are going slowly. So shift operations, now ARM has shift operations, but they are not separate instructions. Now it's like you don't have a separate instruction to perform a shift. That is because these shifts are embedded into data processing instructions. So ARM offers the ability to shift the second operand as a part of any data processing instruction. So that's how ARM instruction set is designed. Now this is useful because shifts are common. They are going to be common in programs, even though you don't specifically mention shifts in C programs written in C. When the compiler does this job, some calculations can be done using shifting. Now that also you will see later. For example, multiplying a value with a multiple of 2, like not power of 2. When you multiply a certain value by a power of 2, then you can use this shifting operation. So so those things, the compiler converts them into shift operations. So that's like an additional note, but here you need to know how shift operations work in ARM assembly. And now here you can see when you are performing an add operation, you have add R5, R1, R2, LSL hash 2. Here, when you are doing this add operation, instead of just adding R1 and R2, so up to this point we have discussed add R5, R1, R2. Up to this point we already have discussed, and this is like a additional part that you add into that instruction. With this, what you can do is instead of just adding R1 and R2 and putting the result back in R5, you can shift R2 2 times to the left. So this that is given in this comment. So R2 you can shift it 2 times to the left and add that shifted value to R1 and put the result in R5. Hope you get the idea. So R2 without just adding R1 and R2, if you didn't have this part, what it will be performing is R1 plus R2. But here when you have this LSL hash 2 at the end of the instruction, what it does is it shifts the second operand 2 times to the left, and that shifted value is added to this R1, the value in R1 register. So that's how it works. And if you like say for example, you don't always get the need of shifting a value and adding it to some other value. Maybe you get the need of just performing the shift operation. So for that you can use this move instruction. Actually, move is an instruction in ARM used to move a value stored in one register to another register. That is, if you didn't have this LSR hash 4 thing, you can move the value in R5 to R6. So that I think that was there in your skeleton codes as well. When you wanted to put a value to a certain register, you use this move instruction. But if you want to like when you want to perform a shift operation, you can use this move instruction. And before moving the R5 direct, like without moving R5 directly to R6, you shift the value in R5 4 times. In this particular example, you are shifting R5, the value in R5 4 times to the shift right, and that value is moved to R6. So the instruction we are using is just a move instruction with this LSR part added. Okay, so R6 will get the value of R5 shifted 4 times to the right. Hope that's clear. And there's another example that shifts. Yeah, instead of just shifting a constant time, like constant meaning an immediate, like without using the shift amount as an immediate value, you can specify that as a value stored in another register. That is, if you want to move, like shift the value in R5, a value like a value times, like this is like R5, you have to shift the value stored in R5. The shift amount, you are not directly giving it as a immediate value, but that value is stored in another register. For example, in this example, it's stored in R3. So R5 is shifted R3 times. So R3 actually is a value, another value which is stored in another register. Here in this example, it's stored in R3. Hope you got the idea. Clear? So that's how shifting works. Bit shifting works in assembly, ARM assembly, to be precise. So they are all going to be embedded in data processing instructions. Move, add, sub, all these we call them data processing instructions. Without having a dedicated instruction for shifting, ARM uses this embedding method. So it indeed includes the shift operation directly inside data processing instructions. But here you can see something different to that idea, because still the assembler supports instructions such as LSR, R6, R5, #4. Here it is left shift right. Now you see there's a separate instruction code for left shift right that is supported by assembler. But when the assembler converts, so assembler is like it still is not at the 1-0 level, binary level, machine code level. It's higher. It's in a higher level compared to machine code. So it has the capability of converting this into a machine code supported by the processor. So machine code actually is supported by ARM processor is going to look like something we saw earlier. So you can write in assembly an instruction like this, but the assembler is going to convert this into a data processing instruction that can perform this shift operation. Essentially, it's going to be something like this move instruction. It's going to be converted into this move instruction that performs moving a register value by after shifting, after performing a bit shift. So this is synonym. So they are synonyms for move instructions with shifted register second operands. So the assembler, when it converts this to a machine code, it converts it into a data processing instruction. Specifically, it's going to be converted into a move instruction that shifts its second operand. Okay, hope that's clear. So at assembler level, you can write in assembly you can write these instructions, but they are going to be converted into move instructions at the end of the day. So shift operations if you look at the way they are encoded in binary, we already talked that they are going to be used as part of the data processing instruction. So condition is there, and then the format is 0. You can see it's 0. Okay, so the 2 bits used for shifting used for representing format is 0 because this is still a data processing instruction, and opcode you have, and then the next bit we have like put it to 0 in hard coded way, and set bit. Those things are similar to what we saw in data processing. The only difference here is the last field of the data processing instructions. So in the data processing instructions, we saw that could be used either for immediate operands or to specify a register number, and that was 12 bits. So when we are using it for shifting as well, like if we are going to embed shift amount as well in the instruction, we are using the first 8 bits of the last field for this shift settings. So shift IMM. So this shift IMM field, we are using it to, like the last field, we have broken it again into 3 subparts. So that we can use it to specify the shift amount and the type of shift we need to perform. So all that you can encode by using these 8 bits, the first 8 bits of the most significant 8 bits of the last part. And you all know that we only have 16 registers, so to specify the second operand we only need 4 bits. So the first 8 bits shift IMM field, how many positions to shift, that is the shift amount. We saw it was like #5, #2, things like that we encoded there, and the shift amount you can put there, and the type of shift type you put in this the second 3-bit field, whether it's a left shift right, whether it's a right shift logical shift left, logical shift right. There are things like shift rotate. So those shift types you can encode, the shift type you can encode here in this field, and yeah, that's it. Now the second operand, the value which is stored in a register, and that is going to be shifted. So that the register that contains the value to be shifted is going to be stored in this RM field. So this is an example. Here is an example of add instruction which performs logical shift left as well. Opcode you have to put here, and RD is here, RN is here. RM is the second operand, and left shift logical shift left, that is so this is going to be encoded in this ST part, and then shift immediate, this value is going to be put in this part of the instruction, and this is the result. And logical shift right also is given here, and yeah, that's it about shifting. And then we come to another very important part, but we have already run out of time for this session, which means that we need to have another extra session. So since we are discussing basic concepts, we are going slowly. If you don't understand these things properly, like now we saw that you had questions about these things. So since we are going forward, clearing out your doubts, we had to spend some extra time here. So anyway, it's okay. An important part is left to discuss. So this condition. So here we are discussing about how something like an if condition can be compiled into assembly. So it's like the most important part of this tutorial too, actually, because we are going to do exercises which make use of these things. So we will stop it here.